Dear students, so today we are going to see the different principles or laws that we have learned in the module 4, which basically talks about kinetics and kinematics. So the first one, so I am putting all those similar laws together. Anyway, one law will be leading to the other, but we are putting the similar laws together. The first one is Newton's second law. We know that from Newton's second law we have the relationship F is equal to ma, which was further modified and was presented to you in the form of D'Alembert's principle, and which says that sigma Fi is equal to MAI. And then we have seen a condition or an expression which talks about the work energy principle. Okay, work energy principle, in which we said that the work done, which is F times D, is equal to change in kinetic energy, that is half mv square minus u square. Then we have the impact momentum principle, impact momentum, which talks about the concept of force times time, or the duration, is equal to change in momentum. Okay, final momentum minus initial momentum will give impact. So when you see all these conditions, you should know that these all are derived from the basic equation, that is Newton's second law, F equal to ma. This you can see there is a direct linkage between these two, the D'Alembert's principle and Newton's second law. Okay, F M A. So it has got a direct relation. Now we are going to talk about this one, F into T, that is work energy principle. Okay, we are going to talk about work energy principle. The equation what we have is F into D is equal to half m v square minus u square, right? Now if you are just reforming this equation, okay, if you try to reform the equation, I'm trying to express this in terms of F. So I'm taking whatever that is on the that is left on the left side to the right hand side. So the expression will be half m v square minus u square by d. And from basic equations of equilibrium, or say the laws of motion, we have the equation v square is equal to u square plus 2as, which implies v square minus u square can be represented as 2as, where s is the displacement. Okay, so when we substitute v square minus u square with 2as, so we have represented the displacement as d here it is s, so I'm just converting this into d. So what I will be having is that F equal to half into m into v square minus u square is 2a. Instead of s I am writing d because both are same displacement. This is also displacement, this is also displacement, divided by d. When I do this operation and reducing this right hand side, d get cancelled, half get cancelled, and what remains is again the Newton's second law, that is F equal to ma, right? Similarly, if I am seeing the impact momentum, okay, impact momentum, what is the expression? F times T is equal to m into v minus u. So now again I'm trying to reframe this equation. So I'm keeping the force on the left side and taking whatever that is left on the left hand side to the right hand side. So it's going to be m minus v minus u by t. Now again we are going to the basic laws of equation that we have. We know that v equal to u plus at, which implies v minus u okay, is equal to 8t. I'm substituting this condition here, so the right hand side becomes m into v minus u is 8 times t divided by t. T cancels away, and what remains is F equal to ma. Okay, so all these equations are basically derived from Newton's second law. So in one case, we are representing the left hand side as work and the right hand side as change in energy. And in the other one, the left side is impact, which is basically force times the duration of the impact, which is given by mass times change in velocity, which is basically the change in momentum. So all these equations are very easy to remember, and you should know the derivation part is also pretty easy, because when you formulate this kind of calculation, you are going to get the basic equation that is told by basic law that is told by great Sir Isaac Newton. Thank you.